Anybody have any homework questions? Yes. Uh-huh. Now I'm not so sure. Okay. Number 5. So we're going to use, so maybe instead of going through this whole problem, I'll just draw the two coordinate systems and we'll talk about how P and R and that kind of stuff changes. Okay, so rotating coordinate system. Number 5. Let's see. So there's a pin joint connected to a rod, and that's attached to a disc that rotates around a point in the center. And the radius of the disc is 1.5 meters. The length of the rod is 1.3 meters. And it says calculate the acceleration of this point P using two different coordinate systems. And it gives angular velocities and stuff. The disk rotates about its center with an angular velocity of -5. So that's well, let me draw the two coordinate systems. So there's one of them. I'll call that coordinate system A for part A. And then the second one is this. I'll call that B. We'll use that one for part B. Okay, so the disk rotates clockwise about the positive y-axis at 5 radians per second. So that's this way at 5 radians per second. And an angular acceleration of +10. So the angular acceleration is the opposite way. And then at the hinge, the rod is rotating with a constant angular velocity this way at 8 radians per second. So in both cases, we're trying to calculate A sub P. For both parts, both coordinate systems, the angular velocity of the coordinate system is 0, -5, 0. And the angular acceleration of the coordinate system is 0, +10, 0. And now let's go into the specific cases. So for part A, is the origin of that green coordinate system accelerating? No, that thing's just changing orientation, but it's fixed to the ground. The origin is fixed to the ground. So the origin is not accelerating. And so we're just going to use the equation that says the acceleration of P is equal to the observed acceleration of P plus capital omega dot crossed with the position vector plus 2 times capital omega crossed with the observed velocity of P plus capital omega cross quantity capital omega cross P. For the observed parts, so, well, before I do that, let's calculate the position vector. So the position vector is the position of the point we care about in our coordinate system. It's a vector from the origin of our coordinate system to the point we care about. So that's going to be -1 radius in the x direction, and then positive length of the arm in the y direction. So that's going to be -1.5, positive 1.30. And then, yep. What? No, that is a P. That's the position vector of the point we care about. And then to calculate the observed velocity and the observed acceleration, those are both going to be circular motion. And so what we're thinking about is that green coordinate system being fixed, like we're ignoring the motion of the coordinate system, and we're just thinking about the motion of that point P according to that fixed green coordinate system. So that point P is moving in a circular path. And so all we care about for these calculations are the R vector going from the center of the circular motion to the point, and the lowercase omega vector, the angular velocity of the arm, and if there was angular acceleration of the arm, we would care about that. So for these, we're going to use an R vector that's equal to, so remember, the R vector is from the center of the circular motion to the point you care about. So that's just going from the center of the hinge to the point P, and so that's just 0, 1.30. And then the angular velocity of the body, the lowercase omega, is 0, 0, positive 8. And then alpha is 0. And then the last things we have to figure out are, so going back to the acceleration equation. We know the position, we know the observed velocity and acceleration. We just have to come up with capital omega and capital omega dot. And we already figured that out. So now we can just plug this all in. Yep.
So if the coordinate system at A was fixed and not rotating, there we would have more components of our observed.
If the coordinate system,
if it wasn't
rotating with the disk, there's really no alternate way to solve this that has ever occurred to me. I mean, so if this thing was fixed,
I'm just kind of asking as a general question. Like there would be more components to that.
Well, if it was fixed, you wouldn't be using that equation. Because that equation is only for a rotating coordinate system. You'd just be trying to piece together this really complicated rigid body problem by thinking about when I first started working on this, to teach it, I sort of thought oh yeah, maybe there's an alternate way if you think about, but I was always there were always terms missing that are coming from, I'm sort of 80% convinced now that there's just really no sensible way to think through it without using a rotating coordinate system. Okay, so now we'll go to part B. And so now we're going to that light blue coordinate system. And even though now the origin is going around in a circle, the changes in the orientation of the coordinate system still follow this. So these don't change. Okay? But now we do have to deal with the fact that the origin is accelerating. Okay, so now we're going to have to use acceleration of p relative to the ground is equal to acceleration of p relative to the origin plus acceleration of the origin relative to the ground. This one is circular motion. This one is motion in a rotating coordinate system. Okay, so let's first figure out the acceleration of the origin relative to the ground. So acceleration of the origin relative to the ground is equal to alpha, I'm going to call this alpha 1 cross R1 plus omega 1 cross quantity omega 1 cross R1. And I'm going to do that because so right now we're using circular motion to calculate the acceleration of the origin. But when we get to this part, we're going to be using the big rotating coordinate system equation, which also has terms in it, the velocity and the acceleration observed in the coordinate system. And that's going to use circular motion with different values than this. Okay. So let's figure out what these are. So R1 we're just trying to do the the trickiest part of all this is at each step throwing out the stuff that's not relevant for that step. All we're trying to do is the simplest circular motion problem we did at the very start, is trying to figure out the acceleration of this point as it rotates around on a disk. And all the other stuff is out of the picture for now. So the R vector goes from the center of the circular motion. Remember, this isn't an origin anymore. This is the origin. So the center of the circular motion to the point we care about. So that R1 is negative 1.500. And our omega, the angular velocity of the coordinate system, omega 1, is, what was that equal to? 0, negative 5, 0. And then our angular acceleration is going to be 0, positive 10, 0. So 0, negative 5, 0. And our alpha 1 is 0, positive 10, 0. And now you can plug those in and calculate the acceleration of the origin relative to the ground. And now the acceleration of P relative to the origin, now we're pretending that that origin is fixed. We're not worrying about that, but it is changing orientation. So what's the motion that we're imagining here? That's sort of, this might help a little bit. Okay. So we've already dealt with the fact that the origin's accelerating, but now we have to calculate that acceleration given that that coordinate system is still rotating. So really what we're doing is, forget about this being a pin, get that pin out of there. We're doing a calculation of the acceleration of that P with this being the fixed point and the disk rotating about this point, So the disk is doing this. Okay. We're throwing out the fact that this point is moving. So it's still, orientation is still changing according to these. Okay. Anybody have any questions about that? Okay, so this is equal to the acceleration of P that's observed in the coordinate system plus capital omega dot crossed with the position vector plus 2 times capital omega crossed with the observed velocity vector of P plus capital omega cross quantity capital omega cross P. We already have capital omega and capital omega dot. Those were the same for both of these problems. So what's the position vector for this problem? Well, now our origin is the blue origin. And so our position vector is just 1.3 in the positive y direction. Okay, so that's different from the position vector we had before. And now to calculate the observed velocity of P, and the observed acceleration of P, these are circular motion. And so what we need is just an R, a lowercase omega, and an alpha. So, you can think of it, so the observed velocity is omega 1. No, this is omega 2, sorry. That's the whole reason I numbered these. This is a different angular velocity crossed with a different r vector. And the observed velocity of P is alpha 2 cross R2 plus omega 2 cross quantity omega 2 cross R2. Okay, so now to calculate these, we're ignoring the rotation of the coordinate system and we're just trying to figure out the velocity and acceleration of P. This was fixed. So now that's just a circular motion around that point. So the vector R2 is 0, 1.30. And the angular velocity of the body, omega 2, is just the angular velocity of that arm, assuming that the disk is fixed. So that's positive 8 in the z direction. And that's a constant angular velocity, so alpha 2 is 0. Now, for doing calculations, I don't think there's ever any reason that it would be useful if you're doing a problem like this. There's no reason that it's preferable to choose this blue coordinate system over the green one. It just adds another layer of calculation you have to do. But I do think that doing it in these two places can sort of clarify what's going on as you move the origins around, what it does to the R's, what it does to the P's. Well, actually, now that I say that, it changes the P's, but it doesn't change the R's. That's, I think, generally true. And I suppose, like, if you were doing this for a project or something and you needed to get the right answer, it's always sort of valuable to figure out ways to calculate problems multiple ways. And then if your answers are the same, you feel a lot better about the answer you got. Any questions about that? So you should go to Valley Fair this summer and go to all the rides that have combined motions like this and calculate the acceleration of a person. Yeah. Yeah, I mean, that's just what a position vector always is. Think of that as a definition of a position vector. I think with this stuff, there are a lot of kinds of calculations where I'm not against sort of having an intuitive, like you do this and you do it by feel or whatever. But with this stuff, I think it's really helpful to just think about everything just strictly in terms of the definitions, And so, like, yeah, the position vector, like, otherwise you just get confused. There's just too many layers of stuff. But you know that what a position vector is, the only thing a position vector is a vector from the origin to the point. And you know that what an r vector is a vector from the center of the circular or spherical motion to the point, And if you remember stuff in that way, you can sort of get yourself out of confusing spots. Yes?
So if you want to go like with a Valley Fair right now,
yeah,
it's like one rotation and then in the same plane with another rotation.
Mhm.
like teacups or something like that.
Yeah.
I don't even know.
In the same plane, it doesn't matter because you wouldn't have to use this approach. I mean, because remember that the key thing here is that you have two motions, and the axis of rotation of one of those motions depends on the axis of rotate. It depends on the motion of the horse, you know. And so the teacups is just that's a sort of a different thing. That's just kind of a whipping motion that you get from when you're in the two rotations just happen to be in the right place relative to each other. But that you wouldn't have to use rotating coordinate systems for that. You just have to use just relative motion, like two circular motions and relative motion. But you could calculate it that way. So this, think of this as only, yeah, what rides are there where you, okay, yeah, right. So something that's rotating like this and then going up and down like that. So yeah, is that like the octopus one? Yeah, that's not a very scary one. Are there scary versions of that? Oh, that's too bad. What? To me, there are. But last summer, on our way back from Maine, we stopped at Cedar Point in Ohio. Oh my God. Me and my youngest boy is 11. I mean, sorry, my oldest boy is 11. And we're like, he's like, let's go on a big one. And there's like a pretty big one right inside the door. And we got on this thing like, oh yeah, sure. And it was like terrifying. I was just like, I got out and I was like, I don't know about this place, you know? And we went and looked at our picture. Like we never buy the pictures, they take the pictures. And my kid is just like terrified. He's just has this look like, ah! And he's like half out holding on to the thing. Like, so yeah, their place is scarier than Valley Fair. But I find the rides at Valley Fair to be plenty scary. Yeah. Okay, any other homework questions? Yeah. Yes, you are, that is exactly right. So you can do this like recursively if you had, I don't even think I'm going to try to draw what you're talking about, but like if you had one thing that was rotating with a fixed axis, and attached to that was a thing whose axis of rotation depended on the first thing, and attached to that was a thing whose axis of rotation depended on that, you could piggyback all these things. The idea then would be you'd use the rotating coordinate system thing to calculate the observed acceleration in the next level down, and then that would be the observed acceleration in, you know, the next level down. And so yeah, you can piggyback this stuff.
Would you start with the smallest cowboy?
You would have to start with the smallest cowboy. Yeah, it's cowboys on cowboys on cowboys, and like horsemen. What are those called? Like centaurs. What? Oh, just the horse and cowboy thing. Like I always say so there's one of these bodies whose axis of rotation depends on the position of the other one. And so one of them's sort of riding the other one. And so there's a horse and a cowboy, but they're talking about if you have multiple layers. Yeah, there's cowboys giving piggybacks to cowboys, and yeah, exactly. Until you get to the horse. So yeah, it's cowboys all the way down until the very unlucky horse. And you can do that with relative motion too, by the way. Oh yeah, we did stuff like that, I think, in linkages. Just keep doing relative motion, relative motion, relative motion until you finally attach to the one that's connected to the ground. Any other homework questions? Okay, so the last topic we're going to get into, and we'll probably make this a little bit abbreviated. I don't want to try to cram as much in before Friday as we can or anything, but I want to talk a little bit about mechanical vibrations. And a lot of our thinking about mechanical vibrations is going to be dealing with masses and springs. Um, um, and I think to a lot of people, it seems sort of odd the focus on springs that you have in early engineering classes and physics 1 and stuff. Like you talk about all these forces that come up all the time, and then you talk about the forces applied by springs, and you're like, wait, the things in the drawer in the physics lab, like there's no springs. I never see springs in my life. Why do we care about springs, you know? And then here we're going to talk about my mechanical vibrations. And again, I'm going to go to springs. Yeah. Yes. Yes, that's a torsion spring, and we will talk about that. Yeah. But so what's the so it's like it just seems like sort of an odd thing, like an odd choice of things to emphasize. But as the people in D-Form have seen, uh, this approach to springs ends up being a pretty good description of what happens with a lot of types of materials. A lot of materials, especially engineering materials, act as springs. And um, so even though you don't have coiled springs all over, um, a lot of the stuff that we're doing calculations with involving springs explain what happens if, when a bridge vibrates because it's made out of steel, and steel has Hooke's law type behavior. And so that's just sort of a hand wavy description of like, stop talking about springs. Let's talk about the real world. But this is the way that we do calculations for real materials. Okay. So mechanical vibrations can occur in any system with what's called a restoring force. And a restoring force is a force that tries, a force trying to return the object to its original position. So, for example, a cart connected to a spring. The spring is providing a restoring force that's always, wherever that cart is, the spring is trying to get the cart closer to where the spring's resting length is, where the cart would be when the spring was at its resting length. Or a pendulum, same thing. Gravity is always applying a force that moves the mass back to, you know, a hanging position, or what you asked about, Evan, a torsion spring that does the same thing. And actually, let me screw up your notes. Let's really make this like a circular mass. I don't know if it's very clear what I'm trying to draw there, but so if this was a horizontal thing, if this shaded part was a solid ring, okay, I'm going to be drawing these the rest of class. Okay, so that's solid. Okay, and say this is horizontal. I guess it doesn't matter. This is vertical. And you rotate it like that, and then let go. This thing is going to oscillate back and forth like this. For 400 years, that's how clocks and watches work, and it's the coolest thing in the world. And then electricity ruined it. Yeah, that's right. So this was, but in pocket watches and wristwatches, that's how you had to do it, because you can't depend on those being in a certain position. Yep, that's right. But what all those things have in common is the force that's applied to the mass is always acting in the direction that to return it to its equilibrium position. Okay, and that's a restoring force. And when you have systems with a restoring force, you get oscillations back and forth around the equilibrium position.
Another non-spring example could be
A float on a fluid. Yeah, that's right. And I guess the reason it doesn't oscillate much is just because of friction. So yeah, that's right. That's exactly right. We'll discuss one degree of freedom vibrations or oscillations. That means the same thing. First, we'll talk about free vibrations. Then we'll talk about forced. Well, if we get through all this, we'll probably talk a little about each of these anyways. Forced vibrations, where it's not just the restoring force acting, there's also an external force that's being applied. And then third, damped vibrations. And the reason damped vibrations is important is for most engineering applications, vibrations are something you want to avoid, and you're trying to stop vibrations as fast as you can. Okay, so let's start with free vibrations. That means there's no external like time varying forces applied to the system. So free vibrations of 1 degree of freedom systems. And let's just think of an example. So let's say we have a wall and a spring connected to the wall and a cart with a mass, little m, that rolls along the floor. The spring constant is lowercase k. And let's choose our x equals 0 position. This is 1 degree of freedom. That means we're only dealing with the x positions. And x equals 0 is the cart's position when the spring is at its resting length. Okay, the way I like to think of this, I don't know, mileage may vary, but, and if you have a way that you learned in Physics 1 that you like, feel free to stick with it. But I like to think of the force applied by a spring as being a pulling force. So think of it as a tension. And it's equal to the spring constant times the change in the spring's length. Okay. And then we'll just go from that basic idea and figure out the signs on stuff and whatever. So what this says is, if the change in length is positive, that means the spring's gotten longer. And if the spring has gotten longer, then that means it's applying a tensile force, so it's pulling on the thing. Okay. And when this, it gets into a different position where the change in length is negative, that negative multiplied by this unit vector changes to the opposite direction. So if you think of it this way, the math works out for itself when the spring, the change in length becomes negative. And then we have the weight force, mg down, and then we have the normal force. And our 0 position, our 0x, is at the spring's resting length. And so what happens when we go into the positive x direction from the resting length? What happens to delta L? Yeah, it goes negative. And so we can change this to so I'll keep the arrow the same, but the magnitude of that force is negative kx. Okay, if you get a positive x, that's the amount of negative change in length you have. Now we can write out Newton's second law. And we have a value of negative kx in the positive x direction. So that vector is negative kx 0 plus 0 negative mg plus 0n is equal to the mass times the acceleration, which is only going to happen in the x direction. We don't care about the y equation, but the x equation gives us ma plus kx is equal to 0. And you can divide both sides by m, not 0. Oh, yeah. Divide both sides by m, and you get a plus k over m x is equal to 0. And then a is just the second time derivative of x. So you get this final form that says x second time derivative with respect to time plus k over m times x is equal to 0. So that's a second order ordinary differential equation. And to solve that, well, if you have no idea how to solve a differential equation, at least you know that if a solution pops into your head, just by luck, it's easy to check whether it works or not. And so by total luck, this has popped into our head, we as the human race. So the solution, okay, any ideas? No, but try x as a function of time is equal to a constant times the sine of the quantity square root of k over m times t plus some constant. That's just a constant, and you know, if you think of, we're taking the sine of something, so in some sense that's an angle, and that's why. So, but that's just a constant of integration. It has to do with a phase shift. Okay, so maybe we'll get lucky. All right, so I'll stop there, but here's a spoiler. We will get lucky. That's gonna work. So we'll take but to check it, just take the second time derivative and see that it's equal to the opposite of this, you know. And so those are equal to 0, and so it works. So this equation is sort of going to be the starting point for our looking at mechanical vibrations. Okay, have a good weekend. Except D4 people, have a good lunch.